Hello, happy campers. We're going to start off by shading this little region in here. And today we're going to talk about Fundamental Theorem of Calculus Part 2. And we're going to see that this is actually going to relate the definite integral of an area, and we're going to try taking the derivative of that to see what that gives us. So we're going to start off by using integral notation to define the shaded region, and that would be the definite integral from a to x of f of t dt. Okay, notice how the x-axis is actually a variable t and the y-axis is f of t, so that's our function. So the definite integral would be from a to x of f of t dt. Now, because the shaded region's area depends on where x is located, maybe we move this x location closer to b or closer to a, and the shaded region is going to change depending on where x is located. We can say that the antiderivative capital F is going to be a function of where that x is located. So let's go ahead, and if we were to take the definite integral of that and just use notation, we would say that the definite integral from a to x of f of t dt, if we were to be given a function and we found the antiderivative, we'll just call that f. Now, using part 1 of the fundamental theorem, it would be capital F of x minus capital F of a. Okay, and the whole idea of this entire section is to find out what happens if you're to take the derivative of that. So we're going to go ahead and take the derivative of both sides, d dx, from the definite integral of from a to x of f of t dt, and then we're going to take the derivative of the other side. And this is going to take me some room, so we're going to go ahead and slide this guy up. And the whole idea is I want to know what this equals. I want to know what the derivative of a definite integral with respect to x is. So if we take the derivative of the right-hand side, this is literally saying the derivative of the antiderivative. So this gets you right back to that. Okay, the little f. Okay, the derivative of an antiderivative gets you right back to the integrand. But notice it's a function of x. And then capital F of a, we're saying a is a constant, so the derivative of that is 0. So this is just going to give us f of x. Now this is kind of goofy because this looks like really weird notation, and by the way, this is the proof of it. But the whole point is to notice that the integrand itself, the function stays the same, but instead of having t as a variable now, when we take the derivative, we've got variable x, and that comes from this upper bound. Okay, so to fill in what we're trying to say here, the final answer of this part right here is going to just be f of x. Okay, so we're getting the function value located at that top bound. Now, is it always going to work that way? Well, there's some minor tweaks on it, but I'll go ahead and show you some examples and then we'll be good to go. Okay, for both of these examples, I'm going to show you the fundamental theorem, part 2, using the full, long, drawn-out version of this. And I'm hoping that by the time I'm done with the second example, you're going to look at these two examples from this page and the previous example from the other page, and you're going to see if you can identify what the shortcut is. Shortcut! Okay, so we are asked to find the derivative of this piece. Now what I'm going to do is I'm going to evaluate that piece. Okay, the antiderivative of the cosine of t is the sine of t. And because this is a definite integral, I'm evaluating this from negative pi to x. So if I take the derivative of this definite integral has now been, we found the antiderivative and we're going to evaluate it. We would have the sine of x minus the sine of negative pi. So again, we're plugging in the bounds, just like we did before. The only new piece to this whole unit is just taking the derivative of our answer. So we're going to have the derivative of the sine of x minus, now the sine of negative pi is going to be 0, so that goes away. And we're going to be taking the derivative of the sine of x. The derivative of the sine of x is the cosine of x. Okay, so it looks like we landed back at our integrand with the top bound plugged in. All right, let's take a look at another example. And first thing that I want to point out is we no longer just have x for our top bound, and we no longer have a constant for our bottom bound. So let's see how that kind of plays into effect here and see how that changes our answer with respect to how the fundamental theorem works. But just like before, I'm not going to show you the trick yet. I'm going to let you figure it out for yourself. So we're going to go ahead and evaluate this little piece in here. And the antiderivative of the secant of t dt. So what function, when you take the derivative of it, gives you secant squared, and secant squared of t, and that is the tangent of t. But it's a definite integral, so we're going to show that we are evaluating it from 3x to x squared. The derivative of tangent of x squared, top bound plugged in, minus the tangent of that bottom bound plugged in. All right, now if we take the derivative of this, this is separated by a minus sign, so we can go ahead and do the sum and difference. And the derivative of tangent of x squared, the derivative of tangent is secant squared of the argument, but now here's the chain rule, times the derivative of the argument. Okay, here we've got minus secant of the argument 3x times the derivative, oops, I forgot the square, pardon me. Derivative of tangent is secant squared of 3x, and then times the derivative of 3x, which is 3. Clean it up just a little bit, and we'll have 2x secant squared of x squared minus 3 secant squared of 3x. And that's our final answer. So your job is to look at the final answers, compare them with the original integrand, and see if you can figure out the shortcut rule so that you don't have to go through all the work. Okay? And we're going to do a lot of practice with this kind of stuff, and then we're going to also do some AP problems with this. So I want you to go ahead and look at your assignment sheet, and this is Fundamental Theorem Part 2. So I want you to go ahead and try some of those in-class problems that go along with this. And I hope you guys have fun. Talk to you later. Bye.